All right. Well, welcome everyone. Thank you for coming to Richard Buzard's PhD defense. My name is Chris Mayo. I'm his advisor. I'm in the Geoscience department. And today we're really happy to see Rich bringing all his work to fruition here. And I'm very excited for this presentation and to hear him kind of respond to your questions. We got to really make sure we show him how to truly defend his dissertation, his work here. His dissertation, titled Coastal Hazard Analysis and Projections for Arctic Alaska Communities, encompasses a number of different works that he has that he's done through the past about 3-4 years. So very excited about that. In addition to me, he has a very esteemed committee. So we have Dr. Ben Jones in the back from INE, Dr. Nicole Kinsman from the National Weather Service. She's online now. Dr. Lee Erickson of the USGS, outside examiner, Dr. Richard Collins, director of the graduate school. We're very happy that Richard agreed to be the outside examiner, and really happy to have him here. He's been a supporter of graduate work and some of Rich's work throughout his time here. So thanks, Rich, for doing that. A few ground rules here. So basically, Rich is going to have about 30 to 35 minutes to present. And after that, we'll have public questions. We'll go as long as those questions last to some degree. Maybe we'll see how long they go. And then after that, we'll kick everyone out and the committee will continue to ask Rich questions and discuss him finishing up. So that's kind of some of the ground rules there. Initially, I'm going to give some opening remarks here. Zoom rules, everyone on Zoom should be familiar with those, but please mute yourself. If you do have questions, you can type them in the chat, or you could raise your hand digitally or just kind of wave around. Alex is going to be monitoring that, so we'll address those questions as they come up. I would say that during Rich's presentation, it will be just a continuous presentation, uninterrupted. We'll save all of our questions till the end, and then we'll talk things over then. So to provide a little context to Rich's PhD, as it's been a long time coming, Rich got here 2015 in August after finishing his bachelor's in environmental science at UW. So Rich came up here August 2015, and that's when we first met in person. And right away when Rich got here, we pretty much about a week later, we climbed into this very small plane with all of our gear and landed in Good News Bay. And I always look back at that because that was actually the first village I ever went to, and with Rich being his first village. And so we really came in there really wide-eyed, like, holy cow, what have we gotten ourselves into? And then really grew to love the work in the villages and love all those aspects, the adventure of it, the being able to kind of collect these new data sets that hasn't been collected before, working with the local people and learning from them, and then kind of experiencing that adventure of, Good News Bay. That time we first went, that was like the best fishing I ever had in my whole life. So all these experiences together really kind of, taught me that Rich is really a great person to work with. And he's also a really enthusiastic problem solver. Rich, you put a problem in front of him and he's going to work at it and with a positive attitude and kind of come out with an outcome that you want. And so in the village, we have to do that all the time when we're working in rural Alaska. And so Rich has, in a number of occasions, have solved these pretty technical problems or communication problems and things like that and kind of move forward. So that was really an awesome experience going out there with him. And we've gone to so many other villages after that. In 2017, Rich published on that work in his thesis. So he finished his master's thesis in 2017 based on that work in Good News Bay. So that was really exciting. And then Rich went on after that to go into the PhD program. And he's been, throughout that time, he's been really successful with funding, more so than any student that I've had. And I should say, Rich was my first graduate student. So he's really kind of taught me to be a good advisor through this process. So we've both been learning. But Rich was awarded the NOAA CFAR Global Change Grant. That was one of the first ones. That was like 12 or 15K, really, a big amount of money for a master's student. I'd like to thank Uma Bhatt for facilitating all of that funding that supported Rich. That was excellent. And then he also got a 2-year Alaska Sea Grant Fellowship, another really prestigious award, and that allowed him to conduct his master's degree as an RA and successfully finish that work. He then was awarded another prestigious fellowship, the NOAA Digital Coast Fellow. That was really a national competition that Rich put in for and successfully won, and then was able to work at DGGS through that. So that was really incredible. Another prestigious one, he got an internship at Sandia National Lab. I think that was just for a summer, but still nonetheless, excellent accomplishment. He also interned at the Alaska Division of Geological and Geophysical Surveys, and then eventually took a full-time position as a geologist 3 at DGGS. So quite a time from when he started his graduate school until now of all these successful things. Usually a student just gets one of those and they're happy, and Rich got 5 or 6 of these. He's also been incredible at publishing. He's done a great job at that. So he's on 8 co-authored peer-reviewed manuscripts. He's got 7 site-specific technical reports and 8 DGGS technical reports on drone surveys he's conducted. So pretty awesome. And what I really love is he's already published 3 out of the 4 chapters in his dissertation. So that is music to my ears there. So a few more things I wanted to mention generally on Rich here is, as a Sea Grant Fellow, he developed the Stakes for Stakeholders community-based monitoring methods. And that was a lot of work that Rich put in. And it's really culminated in this program that now is actively working in 12 to 15 rural coastal communities. Those methods have been evolving and improving, but the core set of techniques and everything was developed by Rich. And I think that's a really strong legacy that he has here in Alaska. Rich has also played a major role in my lab. So as he's learning, he's also teaching. And so he's continued to help undergraduate and other graduate students with all kinds of technical issues, with different things with their degrees, and just really been a key member of the lab and really contributed to the ACGL's growth and expansion. Let's see, I also wanted to thank some of the people that have really mentored Rich. In addition to me and his committee members and other folks, I did want to mention, how much other people have contributed. And most notably, I wanted to mention Jacqueline Overbeck, who formerly was at DGGS and now is at NOAA. Jackie really took Rich under her wing and as a Digital Coast Fellow, as a employee, and really honed his professional and technical skills and kind of shaped Rich into who he is today as this really incredible professional ready to go tackle some of the challenges here in Alaska. So I want to thank Jackie specifically for that. I also want to, make special note of his relationship with Alex, who I remember bloomed at the pub so many years ago. And really, I think the success of a PhD student really has a lot to do with their partner. And if you have a strong partner, someone there to support you, you're much more likely to be successful. So I did want to thank Alex for helping Rich be successful at all this. And I think that is it. So I will now present Rich, and he will present his dissertation. Again, keep your questions to the end. And let's have it.
All right. Okay, yeah, I've got my lapel mic on now. Well, thanks, Chris, for that introduction and making my wife cry. Let me figure out the lights really quick here to get, that should work. Okay. Thank you all for coming to this defense and a nice little lengthy introduction there. I've got quite the presentation for us, so I've got to sort of jump right in, and I apologize, it might go over a little bit. So today we're going to talk about coastal hazard analyses and projections for Arctic Alaska communities. And before we get too crazy, I want to thank all my funding and support over the years. As Chris mentioned, there's been a lot of organizations, agencies, fellowships, things like that that have directly or indirectly supported this work. And it, of course, couldn't have been done without them. So the motivation for this dissertation is coastal hazards in Alaska. In 2019, the Army Corps and the university worked together to put out a statewide report of the combined threat of erosion, flooding, and permafrost. And on this map here, actually just a sec, I want to make sure, is my mic working? Everything online is good? Okay, cool. Yeah, so let me know if there's any sort of thing going on with that. So on this map here is showing all of the communities in Alaska and their threat from these three major hazards that can happen. And you'll notice the West Coast and up on the North Coast is where all of the hot colors are. These are the bad threats. And so the motivation for this work is to understand more about these hazards and what's causing them. And some of the issues we find are that communities are built in hazard-prone areas, and also the hazards themselves are worsening due to climate change. And the communities and their supporting organizations need decision support tools like hazard and exposure maps. So these are the chapters in my dissertation that we'll go over. The first two are about erosion, and the last two are about flooding. And before we get into them, I want to explain more about the communities that we work in and the type of work that we do. So this is a community called Kotlik, and they're here on the west coast of Alaska in the south part of Norton Sound. And I just want to point out a few things that are common across many communities. First of all, there's a bunch of buildings. People live in houses, and some of them are older, some of them are newer, and they'll generally be in rows or scattered about. And then there'll also be some larger structures, like this here is a school, and near it is a fuel tank. And very large structures like this construction here, this big old airport runway, often like the length of an entire community. And these strange rectangular ponds, these are wastewater treatment ponds that are generally the way that that is treated in remote communities. And you also notice sort of one main road coming through town. It's actually a boardwalk. Many communities are effectively what they call boardwalk communities. There's no roads, or there might just be a gravel road. And you'll notice there's no highways or anything. You can't drive here. And if you want to get supplies, you get them in from a barge or a small plane. And that is sort of the definition of remoteness. And so the folks that live in these communities rely a lot on fishing, hunting, subsistence activities, as well as supplies that come in. And generally, there's some vulnerabilities that can be very unique. Like there'll be one power plant station. They don't have like an outside power source, which means that they have that sort of vulnerability where if that one critical piece of infrastructure is damaged, then it affects the entire community. So, oh yeah, I apologize. My switch from my computer to this computer changed some of the font sizes. So also I want to talk about culture, rights, and capacity in Alaska. So in Alaska, there are over 200 tribes that make up about 40% of the tribes in the entire United States. So there's a lot of groups. And of course, they have a long history of living in Arctic conditions. These are the people that first came here. So they've been here a very long time. But also there have been several centuries of colonization activities. And this picture, I think, really encapsulates a time when colonization was really taking hold in the early 1900s. And this is in Meshik, which is now called Port Heiden. And there's a bunch of children standing in front of a bara, which is like a traditional sod hut half built into the ground. And behind it is a very Western style structure of materials that would have to be imported in. And so while there's been a lot of changes in the last few centuries, there's still a culture of subsistence in these communities. And it's all about sustainability. It's about that balance of society and trying to live, but also not harming the environment in a way so that we can still extract resources and live off the land and be healthy. And it's been a really long fight and balance of rights, justice, colonization, and also resource extraction. And it's been an interesting history here in Alaska. When Alaska was founded as a state, Alaska Native peoples, the indigenous peoples of this area, didn't actually have rights to own land. And that has been a continuing battle for a very long time. It's over a century where indigenous peoples effectively had very little to no rights about land ownership until the discovery of oil. and they needed to build a pipeline through the state. And that's when the Alaska Native Claims Settlement Act came in the 70s, which started a bunch of Native corporations and really sort of sprung land right ownership back into the hands of tribes. And as another example, if you've heard of the Pebble Mine project, which is a proposed mine in Bristol Bay, very controversial. The groups in Bristol Bay have been fighting for a very long time against that mine, and they've effectively nullified the chance of it being built. And just a couple examples of how it's been this balance of trying to live off the land and be in a modern world, but also maintaining subsistence and culture. And so through this presentation, we're going to focus on disasters, which is a negative topic, but I want you to be aware that there's a nuanced cause for disasters. It's not always just a big storm or whatever that happens. As the US government found, in many cases, Native villages occupy their current precarious locations because the federal government built schools in what were seasonal encampments, and they mandated that Alaska Native children attend those schools. And here's a picture of the school in Napakiak. We'll learn more about it later. But in September, there was a big storm that came through and flooded that whole area. So as an example, so as we go through, some of these results are going to look bleak, but I want you to also be aware of the adaptive capacity that is found in communities. And the truth is that before modern infrastructure, that's a lot harder to deal with these days. Many communities relocated themselves. And as an example, I was in Quigilagok, and the folks there were telling me about how in the 60s they had a really bad flood. About half the community just strapped their houses to their dog sleds, and they just went for miles off into the tundra to the nearby community of Kong to move to high ground. Can't do that today, but it's a pretty remarkable story. Also in 2004, Newtok, which has the fastest erosion rate in Alaska, was found ineligible for disaster aid because they hadn't measured the erosion that was happening in their community. So they actually started an erosion monitoring program with stakes and measuring tapes, and that became the basis for our Stakes for Stakeholders erosion monitoring work. A third example here is in 2007, there were community leaders from Unalakleet, Kivalina, Newtok, and Shishmaref that actually funded their own trip to go to Congress and testify about the hazards that they've been experiencing. And this kicked off a lot of funding to come up to Alaska and deal with Alaska coastal hazards, and actually led to the inception of the coastal hazards program that I worked for. So the point of all this is that effectively the folks in these communities are the ones that have started and created all of the work that I'll be presenting today. And working with these groups, what I've discovered is that Alaska Natives are, as my buddy Andrew would say, "nay tough," and they're a really resilient bunch and really happy to get the work done. And so we found, there's ample capacity and determination in villages to solve these problems, but at the same time, the issues are becoming more challenging, and it requires collaboration to solve them. So when we go to communities, us scientists will go with our fancy jackets and all of our equipment, and we'll get into these tiny planes and fly out, usually a couple plane bounces to get out to these small villages. And then we will meet with community leaders, environmental coordinators, and work directly with them, going around surveying, asking questions about like the history of erosion and flooding, and documenting everything we can. We also like to set up sensors, flood staffs, water level sensors, and monitoring programs. In some communities, we even work with the students there or just their environmental coordinators and set up community-based monitoring. We also, our time is valuable and it's expensive to get out to these places. So when we're there, we work hard. You get that midnight sun and you get to work all day and all night long. So we survey everything we can. And on top of that, we bring our drones and we like to do drone mapping, making imagery and elevation models of the communities. So we'll go into chapter 1 here. And this is focusing on Port Heiden, which was formerly known as Meshik. And the goal of this study was to measure erosion and identify the drivers of geomorphic change. And Port Heiden on this map here is in Bristol Bay in Southwest Alaska. And the communities in this yellow area, that's where Meshik used to be. And the community has since relocated here where this old air base was. So we need to learn about barrier islands before we get too involved because it's a big deal in this story. So barrier islands are landforms of deposited sediment that are often found at embayments or parallels to the mainland. And here's examples of them on the Seward Peninsula. The whole area here is just a slew of barrier islands and barrier beaches, barrier spits. On the north coast, there are a ton of barrier islands. And in fact, the northernmost point in Alaska in the United States is a barrier spit. And they're called barriers because they protect us effectively. They absorb storms and protect the mainland. And that's what was going on in Meshik. This image is from 1957. And this barrier island here is over a mile long, and there's a slew of others, and they actually protected the coastline from big storms and wave energy. But we also build on barrier landforms. There's a picture of Shishmaref, which is on a large barrier island. And it's not just in Alaska. This is all over like the US East Coast. The whole place is paved over barrier islands. So we rely on them for not just protection, but also the ground that we build on. And natural barriers, they can be stabilized by vegetation and soil. And I put that in quotes because that's generally over maybe human timescales are stabilized, but in reality, longer timescales, hopefully, barriers are dynamic and they're always changing due to sea level rise, storms, the sediment budget, currents, sea ice, human activity, and I'm sure many other factors. So the point being that we want them to be stable, we rely on them being stable, but by nature, they are not stable landforms. So this is a picture of what Meshik looked like in 1977. And I'll point out a couple of things here. So there's a bunch of structures, mostly residences, found along this lake. This is called Goldfish Lake, shaped like a goldfish. Here's two big fuel tanks. And then there's more houses. This road goes out to more houses that are out of the frame. House right here, right against the coastline. And then these roads that go out. So this is where an old army base was from World War II. And that's where the community eventually relocated along that road system. So bear in mind how much land is currently between the bay here and the lake, because 40 years later, that land is gone. This is how the area looked in 2017 when we went there. And there are 3 houses left. All the rest had been relocated and a few were lost to erosion. They actually had to build a new road closer to the lake just to move the remaining structures out of town. And you can see some concrete pads where houses used to be. So of course, a lot of change has happened there. And we looked into a bit more, looking at very old maps of the region. And we found that Meshik had protective barriers and a stable coastline for as long as we can look back in time, as long as we know. This map here shows the black dot where the location of Meshik was, and maps going back to 1828. They're a little shaky because people didn't detail every single piece of the coastline, but they generally show the fact that barrier islands persisted across this bay over this time period. And it wasn't until between the 50s and the 70s that the islands started disappearing. So this graphic here shows orange bad, the erosion of the islands as they sort of diminished, migrated a bit inland, and then between the 70s and 80s completely disappeared. And that is when the erosion kicked off. And so the Army Corps visited pretty early on when erosion was happening and found that, of course, it was a big problem. And the biggest problem being that many structures were built right on the coastline because it was a stable coastline. And then these storms would come, and a single storm could erode 30 feet or more of coastline. And that would be, of course, very destructive for these structures, undermining them, bringing them onto the beach and destroying them. And a few examples of the issues that this caused, obviously the first one being structures destroyed. In fact, there was one storm in '78 that destroyed 3 houses overnight. But other issues, they had to move 2 graveyards, one of which was a mass grave from the early 1900s influenza epidemic. And in the image in the top right, the residents actually had to go out on Thanksgiving Day and move this burial ground before a storm came in to erode it, because there was a storm forecast to come in that night. In addition, even though most structures had been moved out by around 2013, there's still a lot of buried waste, including military waste. This base held between 2,000 and 5,000 people and created a lot of waste, and also septic tanks and wells and things like that were buried, keep eroding out and need to be cleaned up. And then in 2020, the lake itself breached, which has changed the landscape quite a bit. So effectively, the community has had, through their relocation, decades of issues going on. In the beginning, they determined pretty quickly that protection in place was unfeasible and they needed to relocate. The process took over 40 years and had to be led by the community. There wasn't a lot of direct aid. People didn't fly in and like give them a bunch of stuff. They had to apply for funding and get the trucks and get the training and deal with all the hazardous materials, like the waste left from the military. So it was a very, very community-led process, which of course is difficult when you're a community of about 100 people. So also, while they relocated and are safer from erosion, the community still relies on marine resources, and they need a safe harbor and a way to access the coastline. So the erosion of the shoreline and the roads makes that very challenging. So we wanted to learn more about the drivers of erosion and provide some insight about whether the coastline would stabilize and allow them to build a harbor. So some of the methods were to measure recent erosion rates. We used time-lapse cameras, community-based monitoring, and GPS and drones. And the top image here shows just 3 panels from time-lapse cameras, and we would draw a profile here and then just measure the distance along the profile with a computer program I made. And then we validate those measurements. These would click every hour, which was really nice. But then we would validate the accuracy using community-based measurements with a tape measure. And then we went about every year, once a year, with GPS and also validated them that way. And so we made this graphic here of erosion with the x-axis being time and the y-axis being erosion rates in meters or erosion distance. And over that 5-year period, we found the erosion rate was about 7 meters a year, 24 feet a year at the site with the old community site. And how that compares to long-term erosion. Well, these are the shorelines that we measured using aerial imagery. We orthorectified about 15 sets of aerial images and drew shorelines on them of the bluff and vegetation line and measured that and measured the distance between them over time using a USGS tool to measure the long-term erosion rates. And at the Meshik site, the scale here, we'll zoom in a bit, but it's about 6 to 10 meters a year. So about what this one is, faster in a few areas. And so our general findings are that erosion rates, they've been rapid since the 70s and they continue to be, they're not slowing down. This graphic here shows the erosion rates around the Meshik area and how in some places for a few decades, they were not very fast on this northern part, but then they sped up and caught up to the southern part where they'd been more consistent. So overall, it can be locally variable, but overall, it's been very rapid. And part of the reason for this is not just all the waves and stuff in unprotected coastline, but it's also the sediments. There's highly erosion susceptible soils from sediments and pumice, and those large rocks there, they look big, but they actually float in water. They're effectively useless for protecting the coastline. And so when the waves come up and reach it, it can erode it very, very far away. And we found that the barriers are continuing to change. There's this big one here called Stroganoff Point that's extending outward. And then this one we've been calling Chistyakov Point that's extending towards the former town site. So they're continuing to change and grow, but there's no growth of barrier islands. There's no return of these islands that would have protected the area. So we don't see any way in the near future that the area would become protected again. And so altogether, these findings indicate that the shoreline is likely to continue to undergo significant erosion, would not be suitable for permanent construction. Fortunately, there's no threat of erosion to the current community location. So this information is useful for planning what to do next about their harbor. They've decided to instead build sort of like relatively cheap temporary roads out towards the coastline to access it, but not like a really expensive harbor that would probably just be damaged. So some of the broader implications of this work. This map here shows the erosion rates that we measured across many communities in Western North Alaska. And you'll see Port Heiden there. I mean, it's in the top 6, but it's not the fastest in Alaska. There's a lot of other communities dealing with rapid erosion rates. And they're considering whether they can protect in place or if they need to relocate. And these communities need erosion projections. We need an idea of how this is impacting them. In addition, there are many communities that have stable shorelines right now, but it may be due to barrier islands. And from this study, we know that if the barrier islands go away, things can change pretty rapidly. And we also know from other studies that sea ice decline and sea level rise will lead to greater barrier dynamism, meaning that they're moving around and changing in currently unpredictable ways. So what I'm hoping is that we could have geomorphic models that would be better about predicting how these barrier islands might change as the climate changes. So before we go to the next 3 chapters, I swear they're a little bit shorter, but I need to do some definitions for you guys, a little bit of schooling. So we're going to define disaster risk. Disaster risk, I mean, if you think about the word risk, it's like taking chances, right? Disaster risk is when there's the potential loss of life, injury, or destroyed or damaged assets that can occur to basically us, individuals, societies, communities. And this potential loss is determined using probability of whether a hazard will occur, whether we are exposed to the hazard, and then our level of vulnerability and capacity. I'll define these terms. But vulnerability and capacity are essentially balanced against each other. And so for the next little part, we're just going to summarize it as vulnerability for now. Because these make up what we call the risk triangle. And this is an idea that your level of risk is represented by the area of this triangle. And it's defined by the hazard, the exposure, and the vulnerability combined. And if you can reduce any of these aspects, you can reduce your overall risk. So if you reduce your exposure, then there's less risk. If you reduce exposure and vulnerability, there's a lot less risk, even if the hazard hasn't changed. The hazard is still very present, but you've gotten farther away from it and you're more resistant to what it can do. So hazards themselves are effectively the natural processes that happen in the world. In this picture here, there's a big storm coming, lots of big waves, erosion happening, a really dangerous situation. And that's essentially a natural hazard, dangerous situation. Exposure is when we or things that we rely on, our assets, things of value, are in that dangerous situation. We're in a hazard-prone area. And this picture here is Golovin, built partially in a floodplain, and so they are exposed to flooding. Vulnerability is a much broader concept of the many, many factors that can make one individual or population more acutely affected by hazards than another. And I use this picture in Chivak. This was a storm we'll learn more about in September 2022 that damaged a lot of boats of the residents here. And for a lot of people in the United States, a boat is a recreational tool effectively. And if you lost your boat, it would suck, it would be expensive, but it's not the end of the world. In Chivak and in many communities in Alaska, your boat is your livelihood. It's your subsistence, it's your fishing and your hunting, it's your travel to neighboring villages to see friends and family. It's everything. And in addition, these are remote communities where it's very expensive to get boats, motors, equipment, all that, everything that was on the boat. And so losing this, to replace a boat in Chivak, I did the math on this, it costs more than half of a median household income to replace a boat. So beyond losing so many capabilities for the subsistence that's vital to this region, I mean, the financial loss is insane. And that's what vulnerability is. So chapter 2 is about erosion exposure assessments of infrastructure in Alaska coastal communities. The goal of this was to provide timely, data-driven erosion exposure assessments. And this graphic here, we'll learn more about how this whole thing works. A big motivation for this was that there's a disconnect between hazards and exposure. By 2019, when we started this, we knew we had this erosion threat report And we knew where communities were feeling the most and the least threatened by erosion. And we also had erosion rates measured from imagery. And so we had an idea of where the fastest erosion was going. And you would think that, well, where there's the fastest erosion, there's the greatest threat. But when we plotted them against each other, we found it's effectively completely random. This graphic showing all those dots are communities, and towards the right would be faster erosion, towards the top would be a higher erosion threat. And so these questions come up. Why are there places that have very slow erosion that are so threatened? And why are there places with rapid erosion that don't seem to be threatened? So to begin to answer these questions, we did an erosion exposure assessment where we measure erosion, we project that going into the future, and then we identify the infrastructure that's in that eroding area, textbook definition of exposure. So we'll start with those drawn shorelines, and we will draw transects across them and measure the distance over time to get an erosion rate. And then use statistics, weighted linear regression to project that rate continuing far into the future. And this is informed by any variations that happen through the long-term periods, to be about 60 to 70 years of historical shorelines. And we'll project that 60 years forward. And due to uncertainties, both mathematical and ones that are harder to account for, we just smooth out the results a bit into these broader 20-year periods to say, as a planning tool, this is an area that in the next 20 years, is definitely likely to be impacted by erosion in some way and moving forward into the future. And so this is what a resulting product of this work looks like for the community of Napakiak. Remember that school I showed you earlier that was all flooded? There's a picture I took of it from a plane when the tide's low. And you can see it's also very threatened by erosion, a big issue that's currently happening for this community. And so this map here shows the historical shorelines in pink scale and the erosion direction there going towards the current community landscape and projections towards the future. And of course, the main result is about erosion and where it's going. But another result that I really like to point out here is all of the land that's not in the eroding area, especially when you get farther and farther away from it. And so that's how these kinds of products also serve as a planning tool. Well, it's not a total disaster for the community. You're going to have to relocate a lot of things, but there's a lot of safer land to relocate to. In addition, we also do replacement cost breakdowns. These were requested by our funders to provide more information and support for this work. And here's a table for Napakiak of the general replacement costs for buildings and the timeline. And then there's further breakdowns into tables of individual items. And that's how those look there, with either just the structures, the length of utilities, things like that. And the folks that use this information are well aware of this, but the replacement cost is far from the total cost. Total cost can vary a lot depending on the location and local capacity to do this kind of work, or if they need to hire outside employees. And as an example, that school is being replaced, and the current budget I found is $58 million to replace that school, whereas our replacement cost here would be 35. So that's just one example of how the total cost can be a lot more. But it's a good start to get an idea of what the level of issue is. So these are all the communities that we did this work in. All of the ones in black are places where we could do an erosion forecast. So they would either have pretty clear bluff or bank erosion where you could draw these shorelines, or they would have maybe more complicated erosion. So we would generally use vegetation lines rather than water lines. If they had like a lot of beach accretion going on, like here in Hooper Bay, vegetation line shows more clearly the erosion hazard to the airport than what the water line would. Some communities are more complicated. Like in Teller, part of the community, we could do the normal erosion lines, but then they also had issues with scouring. And this is from a November 1974 storm that pushed so much sediment through the community that this is a garage door and there is gravel up on the roof caving it in. So the model we have here is very simple, cannot account for that. And then there's some communities where we couldn't do a forecast because there's been so much mitigation, which is good for them, but it means that it would take more of like an engineering analysis on how well their seawall is holding up to figure out what the potential risk is there. And so on the bottom here, I just gave that we We put out 48 reports in total across this region. And here's a colorized result of the general level of exposure. And it's kind of a weird statistic, but basically the red ones there are Newtok and Napakiak. They make up 50% of the total exposure in this entire region. So if you were to really like encapsulate all those replacement costs, those two communities alone have way more exposure than any other. The brown ones make up the next 40%. So all of those combined are about the same as Newtok and Napakiak. And then it goes down from there. And here's a nice wheel to also visualize how that looks. And so this is actually, I think, you know, when you hear about some communities that are like, oh my gosh, are we going to be the next Newtok or something? Then I think that this kind of puts it into perspective that most communities are not nearly as bad off as some of the ones that you hear in the news. So in summary, this was the first attempt to forecast erosion for many of these communities. It was systematic and equal weight. We also updated it for shoreline protection structures. And some of the feedback we got is that it supports the local observations. It was going to help start long-term planning, recognizing the erosion issue. But this level of work requires updates. It'll eventually become outdated as communities change. And we also need non-linear erosion models, because this is a very simple linear erosion. But then there's things like sea ice decline, storminess, sea level rise that will cause non-linear erosion, as well as reshaping of the coastline and other erosion issues like scouring. And in addition, the infrastructure data that we had was fantastic, but it did not include things like subsistence equipment and storage areas, subsistence use areas that are very critical for communities. So future studies should definitely be incorporating that. Okay, chapter 3. This one's shorter, don't worry. So this was done for 6 communities, and the goal was to improve our understanding of flood risk to support planning and forecasts. When we started these flood assessments, there was pretty limited data available to the National Weather Service to forecast storm impacts. They essentially had this manual that would tell them when a storm comes this direction at this speed, it generally causes this level of flooding. And that just doesn't cut it all the time. In addition, most communities didn't have well-documented flood history or floodplain map. And so it's difficult to communicate these flood risks and also for communities to be able to understand it quickly. And the way that flood risks are often communicated is through categories. It's minor, moderate, major, which indicates a level of impact that might happen. And we define these these are Weather Service definitions that we tailored into a questionnaire that we would try to answer. So major flooding is, of course, the worst level of flooding when there's several buildings flooded. You could have fuel and power generation that are damaged, so power is lost to the community, inundation of the airstrip, things like that. Moderate flooding is still fairly bad. There can be a lot of buildings flooded and areas to the town cut off, but it's usually in moderate flooding, it might be really bad for individuals, but it's not generally like a community-wide disaster on the level of major flooding. And then minor is those low-lying areas. Usually buildings aren't flooded, but these can also still be very impactful if there's a lot of like subsistence equipment left in low-lying areas. So we'll go into communities and we'll meet with leaders and elders to discuss the storm history that they've had and the level of impact that occurs. And then we go and measure all those things. So we measure we try to answer these questions with our GPS and with elevation models. And we also put together a storm history based on where water levels have reached in the past. And all of that comes into this. This is the result. This is a flood staff, and it shows feet above the high tide line, mean high or high water, way up. And then the colors are the flood categories that we decided based on the infrastructure heights. And then the blue lines there are the heights that storms reached in the past. And it's, of course, accompanied by a map. So the yellow area in a minor flood would flood all of that yellow area, moderate would go red, etc. And this also has a table of more like clear levels of what happens at different heights, what kind of infrastructure is at different heights. And fun tool, we don't always know how these things are going to work out until we put them into action. And in September 2022, we found out. So this Typhoon Merbok came up through the Bering Sea and caused record flooding in many communities. And here is a forecast. This is a public forecast that's available of what was going to happen. And the forecast showed that the water level was going to reach 12 feet above mean high water, plus there would be waves that make it go a little bit higher than that. And you'll see on the staff on the right here, 12 feet, well, that's the record flood in Golovin. So according to the forecast and this thing, both publicly available, connected through that same tidal datum, you can very quickly understand this is a bad event. And unfortunately, that's what happened. Here's a picture taken from the school of the flooding in Golovin. I put a blue cone there of where it's looking out. And see that area where the purple goes away where it's looking? And that area in the picture, it's just water all the way. And those are the waves that are exceeding the record flood elevation and overtopping that part of the landscape there. So new record. After this event, the Weather Service really thanked us profusely for making these products because apparently they were invaluable for communicating the hazards that were going to happen and preparing communities for this incoming storm. And that was the goal. We wanted to assess the Weather Service forecasts, and this work is being continued by DGGS. It's being conducted for a lot more communities. And in addition, we're adding a lot more data sets to it, like first floor surveys, getting LiDAR, water level sensors, bathymetry, things like that. So there's a lot of progress being made and a lot of value found in these projects. Okay, last chapter, we're doing it. I'm going to apologize. This one's got some statistics for us I saved for the end. So, you know, there will be a test, but we'll make it through. So the goal for this last project, it's called Storm Surge History, Floodplain Mapping, and Sea Level Rise Projections, Highlight Substantial Risk in Alaska Communities. I normally don't like to put things like that in my title, but you'll see why I did. The goal of this was to quantify regional flood exposure to support mapping and mitigation priorities. And here's a map of all the places that we try to do this work in, which is pretty much every coastal community in that region. So just so we know, this is an area with a lot of storms happening. This is a picture in 1900 in Nome, where a whole mining camp, this is like the gold rush starting, and this whole mining camp built out on the beach there, destroyed by a storm. That's a boat on the left that's just broken in half. A big storm came through, the worst storm ever seen. And then in 1912, another big storm came through, and this was the worst storm ever seen. And in 1913, Front Street got eroded and all these structures were destroyed in the worst storm ever seen. I think you kind of understand the trend here. 74 really was like the worst storm ever seen. And then 2004, more flooding, and 2011, more flooding. And then in 2022, I think this may have actually been a record for Nome. So literally the worst storm ever seen. And you get an idea that these storms happen. It's been a continuous thing. It's a stormy area. There is a lot of hazards, right? But remember our risk triangle. And the leading cause of flood disasters, not just in Alaska, but across the world, is really due to building in floodplains. It sounds like circular logic, but remember that quote about how communities in Alaska were effectively built in floodplains. And here's a picture of the Aluknuk School in the 70s being flooded. This happened all the time. So historically, indigenous peoples of Alaska would often have fish camps. And these are some pictures and drawings. That top one is a drawing from the 1700s of what a fish camp would look like, where you take an umiak, big boat, and flip it over, and you might have some tents and things, and that would be sort of a summer camp where you do your fishing. And then in the winter, you move to other places, you do subsistence, and they would have permanent structures in other locations that would be at higher ground and safer outside of hazard-prone areas. And then when the school system came in and other things, a lot of like, you know, fuel access and the modern things that we enjoy today came in and kind of made communities consolidate and decide on one location to stay. But that location wasn't always the best. Here's a picture of that Aluknuk School 40 years later, eroded and destroyed. And while I was there, I was talking with residents, and they explained that Aluknuk is Yupik for either the wrong way or wrong side or mistake village, because the school was built in a hazardous side of the river. They even found a writing from an early missionary in like the 1900s that said, He said, wow, this big storm came through and it completely flooded the school and my house, but somehow all of the residents, none of their houses were flooded. And it really points to, these anecdotes. But again, indigenous peoples have been here a long time, since the beginning, and are well aware of the hazards that happen. But then there are these things that are effectively out of their control that have led to the modern situations today. So how widespread of an issue is flooding right now is a big question. And also, if we don't move out of these floodplains, how are these conditions going to worsen? And we know climate change is worsening hazardous conditions from sea level rise, protective sea ice is disappearing, and we're getting warmer waters energizing storms. That's actually what happened in September. Normally storms like to curve off and go into the Gulf of Alaska, but the Bering Sea has been so warm that it's very inviting to these storms and bringing record events. So the method for this was to first create a database of known flood events using a lot of sources. And for time, I'm just gonna skip through a bit here. So we also estimate record flood levels in every community, or at least gather the ones that have already been estimated in every community, and then use structures to estimate the exposure to flooding. And here's a little diagram of how that might look. So here's a community up on a hill surrounded by water, and there's a normal maximum tide line, and then sort of their floodplain. This is their level of record flooding, where most of the community is built above the floodplain, and so their exposure is relatively low. But then we have a fourth component. We're going to estimate the exposure given sea level rise projections and see how that changes the situation. So results at a glance here. On the left is just a table of all of these record flood levels. And so these are like that Golovin example. These are those record flood levels that will tell us if an incoming storm is forecasted to be effectively a new record event. And this is also how FEMA defines floodplains. Your floodplain is defined on how high the record flood level is. And then on the right is a map of just more of a qualitative view of the highest flood disaster experience that communities have had, purple being major and then moderate and minor. So a lot of purple going on. And so for that first question, how widespread of an issue is flooding? I have some summaries for all these communities. In yellow are the places that I could do this for that had a record flood and an elevation model and structure data. And then this graphic here shows the colors are the percentage of the community that is flooded. So 75 to 100 means like the entire community would have flood water of some level through it. And just as there's lots of ways to look at these statistics, but I'm just going to choose a few. There are 15 communities that have more than 50%, more than half of the community is within a floodplain. And we're also going to look at depths a little bit. So bear in mind, we're using a metric called depths at structures, but it can represent many things. Here's a picture in Kipnuk about how there's lots of things around structures. So while the homes are elevated, there can be snow machines, four-wheelers, there's boardwalks, there's subsistence storage and equipment. And so I'm using structures for this because that's the data that I had, but it does represent a lot more things of value for the community. And I'll make this easy to digest for now, but here's looking at those depths. Each increment there is 1 foot more of depth, and that little blue square there just indicates how there's 3 communities that have more than half of the community would have 3-foot depth in a record event, which can total four-wheelers and all of those important subsistence vehicles and even flood low-lying homes. So the second question, if we don't move out of floodplains, how will these conditions worsen? I put together sea level rise projections. I summarized them here for the presentation, but in the paper, they're a bit more spread out across the state. But under low emissions, which are very likely to happen as a minimum, by 2100, we're seeing 1.5 feet of sea level rise. And under high emissions, which also have a fairly good likelihood of happening as sort of a maximum, by 2100, we're looking at 3 feet of sea level rise. So 1.5 and 3 feet are the numbers to consider here. And looking at those back on this table, now we're expanding out. And the right of 0 here are structures that are basically just above the record flood level. And we see that there's an increase from 15 to up to 17 to 20 communities where more than half is in the floodplain. And for those areas with the 3-foot depth, it's an increase from just 3 communities to between 8 and 15 that would have 3 feet of depth, which is a pretty big deal. And in total, just looking at percentages of all of the structures across this whole region, currently there's 22% of the coastal community structures are within a floodplain, and that'll increase to 30% under low emissions and 37% under high emissions, which would be a 68% increase. And I'm gonna also compare this to state and global. I'm almost done, I swear. But just keep in mind, this study area is huge. It's bigger than any state. It's like 80% the size of Texas, and it's larger than all but 50 countries. So this is a very big region. And in a question of how it compares to the nation and other countries, about 5 to 10% of the US population is in floodplains. And globally, about 20 to 24% is estimated to be in floodplains. So these values here, 22, 30, 37, these are staggering. So in summary, there's substantial flood exposure in this region of Alaska, and this will be worsened by sea level rise. And I want to remind you this, of course, it's a very simple first glimpse at flood exposure. And I think there should be future work in this direction that also includes increased storminess with the warming waters, sea ice decline, and of course, cataloging the assets representing community values, as well as more dynamic flood models, because this is just a static map. There are many organizations working to bring advanced models to Alaska. So there's some light at the end here. And the communities, they're well aware of the flood hazards, and they have a lot of capacity. They're making strides to develop outside of floodplains. So in conclusion, we know there's many communities that are built in hazardous areas. The costs to deal with these are rising, and climate change is anticipated to be worsening our hazards more than we've previously seen. But there's more analyses and data sets that are becoming available to address these issues. The communities demonstrate adaptive capacity and leadership, and there's growing attention and support to support these communities from outside agencies and organizations. So my personal conclusions are that now is a critical time to be making informed decisions about future development. And with new data sets that are coming to Alaska, we can really start bringing advanced models to rural Alaska. There's been a long-standing issue of a lack of information, lack of data, and that's very rapidly not becoming a good excuse anymore. It's time. Last one is that research should focus on community priorities. That's what we've been striving to do, and there's always improvements that can be made. It should always accompany problems with solutions. So it's not just a doomsday report. We talk about those safe areas and what are the solutions to these issues. And also incorporate the local situations and values like those subsistence assets. All right, we made it. Thank you so much for coming. Of course, I have to give special thanks to my advisor, Chris Mayo, who, as he said in our introduction here, really taught me everything there is about working out in villages and working hard, having fun, catching fish, and getting it done. And of course, Jackie Overbeck, who also taught me many of these values and really helped me publish a lot of this work. And together, you know, their love of fish and their love of dirt and their love of getting all this work done has been a huge driver in this work. I also have to thank all of the people that I've worked with in the communities over the years, the elders, the environmental coordinators, even the children that we've worked with, and all of my coworkers, interns, graduate students. It's just been an absolute blast going out to these places and getting these things accomplished. I have to thank my wife, Alex Yetzi, who's the crab in my crab when I'm feeling crabby. She brings the wine. And as Chris alluded to, she's the real smarty pants in the relationships, always reminding me of things I constantly forget. And you know, we've had quite the adventure together. She even took me on a nice, all expenses paid trip to Italy to go fly drones around a volcano. Best time of my life, just fantastic. And you know, she teaches me to enjoy the fuzzy things in life. Here's our late guinea pigs, Cosmo and Juno, and our newest addition, our Pertato, Luna. and who has also been by my side through this entire dissertation, clinging on for dear life, and probably typing some things and changing my presentation, as cats tend to do. Lastly, I'd like to thank all of our friends that we made up in Alaska. It's been such an experience meeting you all and getting to go to all these new places, and it's a lot of fun. A lot of these folks have been moving down to our area, so we continue to get to hang out. And it's just been such an incredible journey getting to hang out with all you wonderful people. And thanks everyone here and online for sitting through this presentation. And now it is time to question everything.
All right, so questions. I'll hand the mic to you if you have one in the audience here. Andrew, here you go.
Hey, Rich, great presentation, really informative. You mentioned, I want to reference a couple slides. One was a slide kind of towards the end of your presentation where you addressed the fact that climate change and rising sea level will likely exacerbate these rates of erosion. And then I want to go back to one of your previous slides where you actually showed some of the process that you use to extrapolate from measurements taken between ortho images in the 50s up through the 70s, 80s.
Yeah.
And today, and that you have what you described as something of a simple model to sort of extrapolate what that will look like moving forward. And I'm just curious, does that model account for what you addressed in terms of climate change, or does that model simply account for, are we talking about a linear model here? Or are we talking about an exponential model?
Yeah, thanks, Andrew. That's a really good question. And it's one that's definitely talked about extensively in the paper. And so really, I called this a model, but I think that any person who does modeling would just laugh at me, because the model is quite a fancy word for this very simple thing. It's really just linear erosion that's measured, and then it's just continued on if that long-term linear rate continues. And in one sense, yes, it actually does incorporate aspects of climate change. And I brought up this picture in Napakiak here. In Napakiak, their sea ice has declined absolutely rapidly. It's been crazy. Over the period that we measured these shorelines, I don't know the exact numbers, but they've lost a lot of ice. They used to actually have a lot of ice jam flooding. That doesn't occur nearly as much these days because there's so much less ice in that area. And I think that the area used to have more permafrost. Now there's effectively no permafrost. And so on the one hand, there's been climate change for a long time. It's been happening already for decades. And the erosion rates have to reflect that because they're historical long-term rates. But at the same time, you get some of the math in here, and when we do the math on these rates in Napakiak, for example, the change is very small between the shorelines. So the long-term rate is actually, it's a very linear long-term rate. And that was actually surprising, but it effectively means that while all the environmental changes have happened over this time, it didn't really speed up erosion, or if it would have, it didn't slow it down. And so that's part of the justification of like, well, we can kind of trust these long-term rates because we can see that they didn't have any major acceleration. But at the same time, many of those impacts, like you said, of like sea ice decline, sea level rise, and warming, those are accelerating. And so in the past, while these things have changed, in the future, they're projected to change even faster. And in addition, Napakiak's pretty far south, but there's a lot of communities that are farther north that may not have seen these changes yet, or seen these changes on the level that they are projected to in the next few decades. And so that's why I think that these are pretty valuable probably for the first 20, maybe 40 years. But beyond that, I mean, that's where we really need these more climate-informed projections to come in, to give us more information about that longer-term perspective, especially in places with permafrost thaw and really reliance on sea ice that are essentially more vulnerable to these potential accelerants of erosion.
Hey, Rich. Yeah, I similar to Andrew there. Just want to congratulate you on your presentation. Sounded great. I had a quick question for you about one of my favorite parts of the presentation being the wrong side of the river. You know, the name of the community, and that sort of, you know, accessing that indigenous knowledge and that being a component of all the work that you did out in these communities. And so I just was hoping for you to, you know, talk a little bit more to what sorts of buy-in you were able to get in these communities, especially with these actual, you know, deliverables, these maps, these models and stuff like that. You know, is it obviously you mentioned the National Weather Service appreciated some of this stuff, but as far as the products and the experience of being out in these communities with people, yeah, I'd just like to hear more about that.
Yeah, that's great. Yeah, I know. That's the challenge with this, is that I can't pack everything into this presentation that I want to. Trust me, this thing would be 5 hours long. Yeah, no, the experiences drive all of it. I mean, we go to communities. When we first started, we didn't really know what we were doing, so we just like brought all of our equipment and just started doing some science and things. And you know, towards the end, in our first time in Good News Bay, it was like our last day there, and then we were talking to some elders, and they're like, "Oh yeah, well, you know, the whole village used to be over here, and then it flooded, and then there was some erosion, and we moved over here." And it started like, we had all these questions for like a week of like, where should we be focusing? Where are the issues? Where is all this stuff? And just talking to the elders answered all those questions. And so now when we go to communities, we plan ahead of time to have those meetings early on, especially with flood histories, so that we effectively, we do a lot of homework about everything we can read on the internet, which isn't always very much. And then we have those meetings early on to discuss where are the issues, what are the challenges that this community needs to have addressed, and then we go from there. So we leave ourselves sort of adaptable to the community priorities, because yeah, those things always come to light. And then I think you were touching on sort of how these products can be used by communities, and that's a constant challenge. And so you'll notice my units were flipping around from feet to meters throughout this whole presentation. Alaska Native villages measure in feet, and I'm sorry, but these products are for them. So, so you know, some of these larger global level publications have to be in meters, of course, but I try to tailor products to be accessible for communities. And like this map, for example, it's not a 6-foot map, it's an 8.5 by 11-inch map, so that anyone in a community that has 2 computers that are hooked up to the internet, which is a common occurrence, they can print out these maps and access them, and it'll be legible. Things like that, and keeping small file sizes. So this, you know, if you don't compress it right, this will be a 30 megabyte file, which can be really difficult to download. But we compress it down to be like 2 to 3 megabytes so that people can actually access them. And so all of these little things go a long way. And while we're there, we'll connect to the internet and make sure that the internet works. We make some online tools and make sure those work, and making people aware. But it is, I mean, it's a constant battle to make sure that you're achieving all those targets. It's really challenging. Yeah, but you know, I guess being aware of it from the get-go is a good way to address it.
Daryl Schaefer. I'm in PhD studies in disaster management. So that's why I saw this and was like, oh, I got to get to this.
Yeah, welcome.
I will be in touch with you because some of your information I'm probably going to be needing to use in my work. One question I have, with the limited existing long-term monitoring sites from NOAA, U.S. Army Corps of Engineers, U.S. Geological Society, how do you correlate or confirm accuracy and validation of each data set with the indigenous knowledge?
Yeah, that's a great question. So, and this is one of those challenges. A lot of people touch on these notes of like, oh, we need to incorporate local and indigenous knowledge to support our research. But what does that look like? I mean, it's really challenging. And in certain fields, I mean, I don't know the answer to that, but in ours, the way that we do that is essentially you're talking to people and you're asking them about like how high water got, where the shoreline used to be, and you're sort of cross-correlating a lot of these like models and projections and measurements with what people have said. And so I guess I could give an example in Shaktoolik. The community of Shaktoolik has a lot of erosion and flood issues going on. And one of the quotes that I found was that flooding has never reached the main road going through Shaktoolik where it's built today. No one's ever observed it going there. And I know that people have been there since like, I think the 1930s. They lived about a mile south and then they moved up there in the 60s to the current site. And so that gives me an idea just from this sort of quote and these observations that their record flood level is below that street, right? And it's not just the people I talk to, it's their parents and their grandparents who have passed down this knowledge. And that's sort of another perspective of this, is that it's not just the individual you're talking to that knows these things. They'll tell you that, well, our elders, when I was a kid in like the 60s, said that that no flood had ever got higher than this. And then when Murbach came through, the water actually did reach up to that road. And so that tells me this was a record event. And then I can validate that. So if there's like sensors or models that were predicting that level of flooding in Shaktoolik, then we can say, we can kind of say whether those predictions might come to fruition and what that would mean for the community. So I mean, it's always challenging to incorporate the sort of local and indigenous knowledge for certain studies, but for these ones, I think it can be pretty clear. It's very tangible when they're talking about locations and impacts. But yeah, I hope that answers your question. I know, but yeah, we should be in touch.
So you said you're always trying to find solutions to the problem. So for example, in this image here, move away from purple to yellow and into the green stuff. But isn't green stuff going to go away too, just 50 years later?
Yeah, that's a great question. And it is, I mean, it's sort of these time scales. So there's human time scales, sort of lifetimes, and structures themselves have a design life. It's usually 50 or 100 years. And so that's what this product was also designed to do. Most erosion projection publications say that you should only project to about half of the input data. And our input data was 60 to 70 years. So we should only project to 30 to 35 years. But we were specifically requested to project out to 60 because our shorelines were a little old. So by the time it would come out, it would be like a 65-year projection or a 55-year. And that would help because that would encompass the design life of new structures. And so with our project partners being aware, the communities and the state organizations being aware of sort of the inaccuracy of these longer term projections, then this product was helping them say, well, don't put anything in that yellow area that you want to last more than 50 years because it won't, for sure. And then on top of that, there's a little thin blue line there. That's the mathematical uncertainty. But yeah, so then, I mean, that's the challenge in Napakiak. So they are relocating their school and they're actually putting it, they're building it out here, I believe, or maybe even farther for the new school. And if you do the math, it's got about 150 years if the long-term linear rate stays the same until erosion reaches that new school. And so, I mean, that's risk in a nutshell. It's that risk of like, we know it's going to be a problem down the road, but in the meantime, that's many generations and whole lives. And we don't have to like abandon our community site and our culture. We get to continue to live. And that's just, I guess that's just society and life. Oh, yeah.
Thank you.
Rich, you mentioned that we're quickly running out of excuses because of the tremendous efforts that have been going on over the last decade in particular to gain data. Where does Rich Buzard see the remaining gaps? Where should we focus our attention to either fine tune the models or to address the issues that are facing rural Alaska along the coast? Yeah,
that's a great question. Where do I see the gaps? Well, I'll tell you one thing. There's a lot of people that work on this that aren't me. They're a lot more in tune. And there's even publications about current data gaps and priorities that you can find that talk about filling these gaps. A few of them, one is, from what I understand, VDatum. In the lower 48, there's essentially an alongshore model of tidal datums, and I think Reese would know more about this than me. But we don't have that in most of Alaska, and from what I hear, that would be really beneficial for flood modeling. We need a lot of bathymetry. Bathymetry is difficult to get, and Alaska is huge, but the communities are really small. And so it's kind of like we just need bathymetry in these certain locations to be really high res, and the rest can kind of be coarse. And I think that's okay. And then we also need LiDAR. I think that LiDAR is one of the biggest missing factors, because that's sort of, it's a bare earth digital elevation model that is the standard for flood mapping. And so that's really valuable. But of course, this is all from like, data scientists, whatever side. I also alluded to the fact that we need to incorporate subsistence assets and values. And in a conversation I had recently, I was talking about critical infrastructure. Critical infrastructure is a definition by Homeland Security. I don't know the exact definition, but it's effectively like any infrastructure that if it goes out, it causes like widespread issues like loss of power, water, heat, that kind of thing. But in communities like in Chivac, the flooding didn't really come up and hit any buildings because they're built on high ground, but wind knocked out power, and half of the community lost power for days. Their freezers thawed out and they lost their food. They also lost their boats, which is the way that they get more food. So Chivac was, although they didn't have flooding in the way that these maps would show, they were probably one of the most impacted communities by the storm in December, having one of the worst disasters due to these other factors. So I think that the data sets we use, like this one that shows this infrastructure, needs to incorporate even more of those values. Those, and I'm sure many more data, all data, we need everything, but those are some pretty core ones that I think we would benefit from. If there's any questions online too, I think that the audio works through here, or you can type them in the chat.
Any more questions from the audience here?
Hi, congratulations, by the way. Great job.
Thanks, Emily.
Just going one step further, this may be like sort of beyond your scope, but maybe you have ideas since you've been in these communities. So you've created this wonderful product, and communities hopefully will use this for their future planning. What are the barriers to using your product? Like, is it mostly funding issues? Like, are there community disputes about how to move forward? Yeah, what are the barriers, and how might communities address them?
Yeah, I mean, that's a good question. And as you point out, it's kind of nuanced in the sense, like when you first say, what are the barriers? I'm thinking about like access, like, oh, you can download it, it's public information. But I mean, one of the biggest barriers is that you have to know this exists, and it's difficult to get the word out. I mean, there's essentially many communities learn everything from Facebook. And so it's kind of like getting, governments and organizations to be like, well, you got to get a Facebook post. It's not like making a bulletin and everything. And so, but then there's also those other issues. Yeah, I can put out a product, and the community can have it and be aware of it, but are they actually going to be able to act on it? And it's a difficult thing to solve. One of the ways that we are addressing it is that we are working with groups like the Alaska Native Tribal Health Consortium, ANTHC. They're a large organization here in the state that helps, it works with communities to solve these kinds of problems, solving erosion, infrastructure, and a lot of other things. Also, the Denali Commission that funded the flood work, they also work with communities and are working to solve these kinds of problems. So it's sort of like this, like we have the scientists, we have the organizations, and we have the communities, and we're this sort of this circle working together to make sure that everyone's aware of the data and of the science and of the publications, and then putting it into action, putting it into use. And so that's, yeah, I guess that would be my suggestion, is that if you're doing this type of work that you think would be really valuable for communities, you've got to just get the word out and get in touch with some of these larger organizations that are really familiar with accomplishing tasks in communities. Oh, wow, we are 20 minutes over.
Any other questions online or in the house here? All right, well, that's going to convene Rich's public dissertation defense. Thank you all for coming. Excellent to have such a good crowd. Nice job, Brooks.